A relatively new form of logical topology is a logical star. At the heart of a logical star is a special hub called a switch. Messages are sent from network devices to the switch. The switch checks where the message should go and forwards it to the appropriate network device. The logical star topology efficiently uses the transmission medium. If network devices are physically connected by a bus topology, messages will always be broadcast to all network devices. For example, one device generates a message and sends it out on the bus. Each time the message reaches a T connection, the message splits and travels in each direction. The process continues throughout the network until the message has traveled to all devices and reaches the end of the bus. With a physical ring topology, network messages travel from one computer to the next around the ring until they reach the intended computer.
In this section, I will look at the OSI model. To understand networking, it pays to have an understanding of the OSI model, as parts of it are used in modern networking. The OSI model, or Open System Interconnection Model, is a network model designed back in the late 1970s. The model itself did not get adopted. However, references are still made to it in modern networking, especially to the names and the numbers in the model. You will find that most network technologies do not match exactly to the OSI model and do not provide an exact fit. However, it is useful when discussing any networking to reference it against the OSI model. The OSI model has 7 layers. Each layer communicates only with the layer above and below it. By doing this, you can change a layer without affecting other layers as long as the new layer is compatible with the adjacent layers. To understand the OSI model better, consider a manufacturing plant. Imagine the first step in the manufacturing plant is to make a part. The next step, put a protective coating on the part. After this, the part is put in a box. The box then has a shipping label placed on it. The important thing to consider is that each step of the manufacturing process works on the previous. For example, you could not apply the coating to the part if you had already placed the part in the box. The OSI model works the same. Each process or layer of the OSI model adds to the previous. The OSI model consists of 7 layers. Each layer handles a different part of network communication. The first is the application layer. This is where the Application Programming Interface, or APIs, are found. Applications call functions in the API to send network traffic. Next, you have the presentation layer. This layer converts the data inputted from the application into a form suitable for transmission over the network. The session layer controls communication between two applications. For example, the session layer may decide on the port used for communication. The transport layer ensures the data arrives in the same order it was sent and is not duplicated. The network layer determines the path used to transfer data across the network. The data link layer provides error checking and creates the packet to be sent over the network. Lastly, the physical layer sends the data over the network media to the other party. To remember the 7 layers of the OSI model, you may want to consider using a mnemonic. 2 popular ones are, all people seem to need data processing, and please do not tell salespeople anything. Take the first letter of each word to help you remember each layer name. A is for application, P is for presentation, S is for session, and so on. The second mnemonic works from the bottom up. For example, P is for physical, D is for data link, N is for network, and so on. To better understand how the OSI model works, consider this. If a computer wants to send a message to another computer on the network, it communicates with the application layer. The application layer communicates with the presentation layer. The communication goes all the way down to the physical layer. As the data goes down the layers, more information is added, such as packet headers and checksums. The data is then communicated across the network over the physical layer. The physical layer can check the checksum and pass the data up to the data link layer. As the data goes up the layers, more data is removed, such as packet headers. When the data gets to the top, all the headers and checksums have been removed, and the data is presented to the application in a way it can understand. As stated before, the OSI model in its entirety was never adopted. However, the layer names and the layer numbers are still used today. TCP/IP is divided into 4 layers and can be roughly mapped to the OSI model. To better understand why TCP is divided into 4 layers, it is a good idea to look at what happens at each layer. At the application layer, you have protocols such as HTTP, SMTP, DNS, and RIP. At the next layer, you have TCP and UDP. Using TCP, you have reliable transmission, that is, packets are guaranteed to be delivered and delivered in order. UDP uses unreliable transmission and does not guarantee delivery or order of delivery. At the Internet layer, you have the choice of IP version 4 or IP version 6. The final layer provides a link to your network media. As you can see, using layers allows you to add and remove protocols and services very easily. For example, you could add a new network card, for example, a token ring network card, to your computer, and as long as the new network card can communicate correctly to the layer above, nothing else needs to be changed. As you can see, using layers makes adding and subtracting hardware, protocols, and services easy. To put the OSI model in perspective, you will see a lot of literature that refers to a device as a Layer 2 device or Layer 3 device. Switches work on Layer 2 of the OSI model. If you consider this small network, the switch is able to decide, based on the destination packet, which device to send it to. For example, packets coming from the computer to the printer would be directed straight to the printer. Packets going to the server from the computer will not be seen by the printer. The switches look at the destination address or MAC address to determine where to send the packet. If you add another network separated by a wide area network, the Layer 2 switch will not be able to route traffic to this network. To route traffic between different networks, you need a Layer 3 device, for example, a router. The router will be able to route traffic between the two networks, as routing is a function of Layer 3 of the OSI model. You will see devices on the market called Layer 3 switches. Don't get confused by this. Remember, Layer 3 devices support routing. Simply put, a Layer 3 switch supports routing and switching. Layer 3 switches perform routing in hardware rather than software, so tend to be faster than routers at routing traffic between networks. Since Layer 3 switch logic is built into hardware, they lack some features of routers. Keep this in mind if you decide to deploy one on your network.
Hi, I'm Peter. In this video, I'll explain the difference between three popular types of network devices: hubs, switches, and routers. Let's start with the hub. Hubs are cheap and simple devices that can connect a bunch of computers to each other, but they're a little wasteful with bandwidth. Here's how they work. When a computer sends information to a hub, it replicates the data on all other interfaces. It works like this. Bit comes in, clones come out. Bit comes in, clones come out. You get the general idea. A hub doesn't know anything about packets, and it doesn't bother figuring out who is supposed to receive the data. No, it just spams everyone. The receiver will get the message, and the other hosts will ignore packets if the receiver field doesn't match their own address. Not bad for a glorified bit cloning machine. Alright, so every incoming bit is replicated on all other interfaces. That's a fairly simple and cheap way to create a network. However, it does cause a lot of unnecessary traffic. If you have 5 hosts in your network, hubs unnecessarily send every packet to 3 hosts that aren't interested. That's a huge waste of bandwidth. Also, keep in mind that other people in the network can see your traffic if they use free software like Wireshark. If you're embarrassed about your addiction to funny cat videos, maybe hubs aren't your best choice. Now wait a minute, there's a better way to do this. If our hub kept a list of where every host can be reached, then it would be able to send every packet straight to its destination without spamming the entire network. That's what switches do. In this example, we've plugged in computer A to port 1 and computer B to port 6. Each network card has a unique address that switches can use to identify a computer. They're called MAC addresses. They're not only used for Ethernet connections, Wi-Fi uses it too. If computer A has a MAC address of 6 times AA, then the switch will know that the computer with that MAC address can be reached on interface 1. In addition, we know that computer B, which has a MAC address of 6 times BB, can be found on interface 6. All this information will go into the switch table. Now, for this example, I will add 2 more computers. Computer C is hooked up to port 3 and computer D is hooked up to port 4. We have our network now. Let's see how it works in practice. We always start with an empty switch table because the switch has to learn where everything is. And in this example, we will send a packet from computer A to computer C. At this point, the switch does not know where C is, so it will just behave like a hub and flood everything. But it's learning. By checking the MAC address in the packet's sender field, it learns that computer A can be found on port 1. It will store this information in its switch table. Now watch what happens when we send a packet from computer C to computer A. Since the switch knows that computer A can be reached on port 1, it doesn't have to flood the entire network. It only has to send the packet to port 1. The switch now knows where computer C is and adds a new entry to its switch table. Hubs and switches are devices that can be used to create networks, but what if we want to send packets between those networks? That's where routers come in. Say you want to send a packet to your search engine from your home laptop. Once you send your packet to the internet, how does it find its way to the search engine server? That's the work of routers. Once you send the packet to your internet provider, routers make sure that your packet is passed on from network to network so that it eventually reaches its destination. If all goes well, that is. You probably have your own router at home too. It forms a bridge between your own private network and the network of your internet provider. Through the network of your internet provider, you can reach the rest of the internet. Modern routers also carry out other tasks. For example, they often do network address translation, or they can hand out IP addresses to hosts using DHCP. We have videos on both of those topics, so just click the thumbnails if you want to watch them. Additionally, many routers can also act as an access point for Wi-Fi. Now that we've gone over all 3 devices, let's compare them. It is worth pointing out that hubs, switches, and routers each operate on a different layer. You may recall from other videos that every packet traveling over the internet consists of 5 layers. The physical layer is just raw ones and zeros. Since hubs just replicate bits, they operate on the physical layer. The link layer is specific to the medium over which the packet is traveling, such as Ethernet. MAC addresses are part of this layer. Since switches rely on MAC addresses to get packets to the right destination, they operate on the link layer. The network layer is where the IP protocol does its job. A packet's source and destination IP addresses are stored here, among other things. Since routers work with IP addresses, they operate on the network layer.
The Internet is a vast network that allows computers around the world to communicate and share information. Huge amounts of information in the form of words, images, sounds, and computer software are transmitted through the Internet. The Internet links computers mainly by the telephone system, through copper wires, optical fibers, cables, or radio waves. Access to the Internet begins with a computer linked to the telephone lines through a device called a modem. Special software is needed to convert computer files into the type of signals that can travel through telephone wires. The signals are then launched into the phone lines through the modem. The phone lines lead to an Internet service provider or a commercial online service, which act as a conduit to the Internet. Computers break the message up into packets, clusters of 40 to around 1,500 characters. Each packet, individually marked with its destination, is then sent through a series of computers called routers that direct the path of the packet. Each router examines the packet to see where it's headed and sends it along the best path to its destination. Packets from the same message may take different routes to reach the same destination. The packets eventually all arrive at the same place and are pieced back together into the original message.